The Sun. It's a giant ball of blazing gas. More importantly, it is the heart of our solar system. Life as we know it wouldn't exist without it. The Sun bathes us in light and warmth. It dictates our seasons. It's the reason we have day and night. Without the Sun, our planet would be a frozen, lifeless rock. But the Sun's influence extends far beyond Earth. Its immense gravity holds all the planets in their orbits. It's a constant presence in our solar system, a force to be reckoned with. We owe our very existence to this celestial giant. Understanding the Sun is key to understanding our place in the universe. It's a fascinating journey into the heart of a star. So, buckle up as we embark on an adventure to the Sun. Let's start with size. The Sun is huge. You could fit over 1 million Earths inside it. Just try to imagine that for a second. If the Sun were the size of a basketball, Earth would be a tiny speck of dust. That's how massive our star truly is. And it's not just big, it's incredibly heavy too. The Sun contains over 99% of the mass in our entire solar system. That's like having a bowling ball in the center of a room and calling a few grains of sand the rest of the solar system. This enormous Caesar mass gives the Sun its incredible gravitational pull. It's what keeps everything in our solar system, from giant Jupiter to tiny comets in orbit. The Sun's sheer scale is mind-boggling. It's a reminder that we are just a small part of something much, much bigger. Now let's talk about what makes the Sun shine. Nuclear fusion. Deep within its core, the Sun is a raging inferno. It's like billions of hydrogen bombs exploding every second. But instead of destruction, this process creates light and heat. Here's how it works. Intense pressure and heat in the Sun's core force hydrogen atoms to fuse together. They form helium and release a tremendous amount of energy in the process. This energy gradually makes its way to the Sun's surface. From there, it radiates out into space as light and heat. This process has been going on for billions of years. It's what fuels the Sun and gives us life here on Earth. Nuclear fusion is a powerful force. It's a testament to the incredible energy contained within the Sun. Imagine you're in a spaceship, ready to journey to the Sun. You might think it's a simple matter of pointing your ship towards it and firing up the engines. However, it's not that easy. Earth is moving sideways relative to the Sun at an incredible speed. To reach the Sun, we need to cancel out this sideways motion. This requires a tremendous amount of energy. We need to slow down our spacecraft relative to the Sun. It's like trying to swim upstream against a powerful current. Only then can we begin our descent towards the Sun. But even with this hurdle cleared, our journey is just beginning. The Sun's intense heat and radiation pose significant challenges. Our spacecraft needs to withstand these extreme conditions as we get closer. Our journey to the Sun is not for the faint of heart. Section 5. The Sun's outer atmosphere, a crown of fire. As we approach the Sun, we first encounter its outer atmosphere, the corona. It's a vast, shimmering halo that extends millions of kilometers into space. The corona is incredibly hot, much hotter than the Sun's surface. Temperatures here can reach millions of degrees Celsius. The corona is a dynamic and mysterious place. It's constantly expanding and changing. Giant loops of plasma called coronal loops rise and fall like fiery arches. Solar flares, sudden bursts of energy erupt from the corona, sending out streams of charged particles into space. These solar storms can disrupt satellites and even cause power outages on Earth. They are a reminder of the Sun's immense power and the importance of understanding its behavior. Our journey through the corona is a perilous dance with extreme heat and radiation. Section 6. Through the chromosphere's shifting temperatures. Below the corona lies the chromosphere, a thin layer of the Sun's atmosphere. This layer, though not as hot as the corona, plays a crucial role in solar dynamics. Here we encounter a strange phenomenon. The temperature, which initially drops as we move away from the core, starts to rise again in the chromosphere. As we descend, the temperature starts to rise again. This counterintuitive increase in temperature is one of the many mysteries of the Sun. It's like going from a hot oven into a blast furnace. The heat becomes more intense, and the energy levels soar. The chromosphere is a region of intense activity. It's a place where magnetic fields twist and turn, creating a dynamic environment. Giant jets of plasma, called spicules, shoot up from the surface like fiery geysers. These spicules can reach heights of up to 10,000 kilometers. Solar prominences, massive loops of plasma, extend from the chromosphere, reaching high into the corona. These structures are held in place by magnetic fields. These prominences can last for days or even weeks. They are a testament to the sun's magnetic power and its ability to shape plasma. Sometimes they erupt, releasing enormous amounts of energy into space. These eruptions can have significant effects on space weather. The chromosphere is a reminder that the sun is not a static object. It is constantly changing, with new phenomena emerging all the time. It's a dynamic and ever-changing star. The activity in the chromosphere is just one example of the sun's restless nature. Our journey through this layer is a constant battle against increasing heat and radiation. The deeper we go, the more intense the conditions become, but the wonders of the sun continue to unfold before our eyes. Each layer reveals new secrets and adds to our understanding of this magnificent star. Section 7. The sun's surface, a sea of granules. Finally, we reach the sun's visible surface, the photosphere. This is the layer that emits the light we see from Earth, making it the most familiar part of our star. This is what we see from Earth, a bright, glowing disk in the sky. But up close, it's a very different story. The surface is not smooth, but rather a dynamic, ever-changing landscape. The photosphere is not a smooth, solid surface like the Earth. Instead, it's a turbulent sea of gas, constantly in motion. It's a turbulent sea of gas, with currents and waves of plasma moving in all directions. Looking closely, we see that the photosphere is covered in small, bright regions called granules. These granules are the tops of convection cells. These granules are the tops of convection cells, where hot plasma rises from the sun's interior, cools, and then sinks back down. Each granule is about the size of Texas and lasts for only a few minutes before fading away, replaced by new ones in a continuous cycle. The constant churning of these granules gives the photosphere a grainy appearance, almost like the surface of boiling water. It's a reminder that even the sun's surface is in constant motion, a dynamic and ever-changing environment. The photosphere is the coolest layer of the sun's atmosphere, yet it is still incredibly hot. But even here, temperatures reach a scorching 5,500 degrees Celsius, a testament to the sun's immense energy. Our journey has brought us face to face with the sun's immense power, revealing the dynamic and powerful nature of our closest star. Section 8. Into the Convective Cauldron. Our journey continues into the sun's convective zone. This region lies beneath the photosphere and extends about 70% of the way to the sun's core. Here, the temperature and density increase dramatically. The plasma in this zone is in constant motion. Think of a pot of boiling water. Hot water rises from the bottom, cools, and then sinks back down. This creates a circular motion. The same thing happens in the convective zone. Hot plasma rises from the sun's radiative zone, carrying energy towards the surface. As it cools, it sinks back down, only to be heated again. This constant churning is what drives the sun's magnetic field. It's also what creates the granules we saw on the photosphere. The convective zone is a reminder that the sun is not a static object. It's a dynamic and ever-changing star. Section 9. The sun's core, an unreachable inferno. We've reached the final leg of our journey, the sun's core. This is the most extreme environment in our solar system, a place where the laws of physics are pushed to their limits. This is the heart of the sun, the furnace that powers our entire solar system. It's a seething, roiling mass of plasma, constantly churning and burning. Here, the temperature soars to an unimaginable 15 million degrees Celsius. To put that in perspective, that's over 27 million degrees Fahrenheit. The pressure is billions of times greater than at the Earth's surface. It's a crushing force that defies comprehension. Under these extreme conditions, hydrogen atoms are constantly fusing together to form helium. This process, known as nuclear fusion, is what makes the sun shine. This nuclear fusion releases the energy that powers the sun. It's an incredible amount of energy, enough to sustain life on Earth and drive the weather and climate. It's a continuous process going on for billions of years. The sun has been burning for about 4.6 billion years and will continue to do so for another 5 billion years. But the core is not a place we can ever reach. It's a realm beyond our current technological capabilities. The intense heat and pressure would instantly vaporize any spacecraft. No material known to man can withstand such conditions. Even if we could survive the journey, we wouldn't be able to see anything. The blinding light and radiation would obscure our vision. The core is hidden from view by the layers of plasma above it. These layers act as a barrier, shielding the core from direct observation. So we must be content with studying the Sun from afar. We rely on indirect methods and advanced technology to learn about its inner workings. We can use telescopes and spacecraft to observe its surface and atmosphere. These tools provide us with valuable data and insights. We can study its magnetic field and its effects on Earth. Solar activity influences everything from satellite communications to power grids. But the core will always remain a mystery, a place of unimaginable power and wonder. It's a testament to the incredible forces at work in our universe.